The first integration technique that we looked at is called integration by substitution, and it's used to undo the chain rule. In this section we'll look at another technique for integration, integration by parts, which is used to undo the product rule. So first we'll look and see how this rule works and where it comes from. So we'll need two functions, since essentially we're going to multiply them together and take the derivative of the product of two functions. So the two functions that we'll consider, we'll call them u and v, and both of these are functions of x. So it's important to remember that u is a function of x and v is a function of x. But in order to make the notation a little bit less messy, we'll just write u and v. But keep in mind that both of those are in fact functions of x. Okay, so here's the product of the functions u and v, and we want to differentiate that product with respect to x. So the product rule, this is an application of the product rule, says that I take one function u, I multiply by the derivative of v, and then I take the other function v and I multiply by the derivative, looks like I made a typo here, by the derivative of u. So the next step is simply to rewrite this first line in a different notation to make things just a little bit easier. So u times v prime is equal to u v prime plus v u prime. That's saying exactly the same thing as this top line, which is the application of the product rule. Next, we'll just do a little bit of arithmetic. So I'm going to solve for u times v prime by simply subtracting v times u prime to the left side. So we get u times v prime is equal to the derivative of the product of u and v minus v times u prime. And then next, we'll simply integrate both sides of this equation. So we'll integrate that term, and that term, and we get this line. Here's the first example. We want to find an antiderivative for t times sine of t. Okay, so notice that the formula, which I've copied up here, says that I want to identify the original integral as u times v prime. These are the parts in integration by parts. And so what I'm going to do is identify u as t and v prime as sine of t. So I've identified u equals t and v prime equals sine of t. So now notice that in the other side of the integration by parts formula, I need to know other information. In particular, I need to know what u prime is, and I need to know what v is in order to be able to carry out integration by parts. So we have to do a little bit of preparatory work. So I've chosen u to be t, and I've chosen v prime to be sine of t. So the first step is easy. When I go from u to u prime, I simply differentiate. So the derivative of t with respect to t is 1. And then as far as v goes, notice that what we've identified is v prime. So this is v prime here, and from that I need to determine v. So that is, I need to find an antiderivative for v prime. Well, an antiderivative for sine of t is minus cosine of t. Okay, so I've done this preparatory work on the side, and I have expressions for u and for u prime and for v prime. So I'm going to take all of these functions and simply plug them into the formula. So that's the next step. Okay, so I've just copied the integration by parts formula here, u times v minus the integral of v times u prime. So then we'll plug everything in. So u is t, I plug that in here. V is minus cosine t, and I write that there. And then v appears again, so v is still minus cosine t, and u prime is 1. Okay, so I've changed this integral into this expression, which includes a new integral. Okay, let's do a little bit of cleaning up before we go further. So I'll just write that negative in front, and so we have negative t cosine t, and I'll pull this negative outside the integral, so I get plus the integral of cosine t dt. And as promised, that integral is much easier to evaluate than the original integral. An antiderivative for cosine t is sine t, and so finally we found the antiderivative. Minus t cosine t plus sine t, plus of course an arbitrary constant of integration. Okay, so again, using integration by parts, the antiderivative for t sine of t is minus t cosine t plus sine of t plus a constant of integration. Let's look at an example where something slightly different happens. Okay, so we want to find an antiderivative for t squared times e to the 5t. So this time I'm going to pick t squared to be u, and I'm going to pick e to the 5t to be v prime. Okay, so remember, what I need to do then is find u prime and v from this choice. So if I pick u to be t squared, then its derivative is 2t, so u prime is 2t. And if I pick v prime to be e to the 5t, I need to anti-differentiate to find v. So an antiderivative in this case is 1/5 e to the 5t. So the first step in integration by parts is to simply plug those values for u, v, u prime, and v prime into the integration by parts formula. So here we have u times v minus the integral of, this is v, and this is u prime. Okay, and just as in the last example, let's straighten up here just a little bit. So in the first term, t squared times 1/5 is t squared over 5. And in this integral, I'm going to pull the 2/5 outside the integral, just because it's a constant, so I'm just going to take it out of the way. So after simplifying, we have t squared over 5, e to the 5t, minus 2/5 times the integral of t e to the 5t. So at this point, I still don't know what an antiderivative for t e to the 5t is, but it sort of looks like the thing that I started with. It's a product of two functions. It's still a product of two functions. And so before I give up, I'm just going to try integration by parts a second time. So this time I'm going to pick u to be t, and I'm going to pick v prime again to be e to the 5t. Okay? So we're just going to go through the integration by parts process a second time. So we've picked u to be t, and we picked v prime to be e to the 5t. So the derivative of u is u prime, which is just 1. And again, v prime is exactly the same as before, so its antiderivative v is also exactly the same as before. So I'll take these four expressions for u, v, u prime, and v prime, and again plug those into the integration by parts formula. So, but be careful, we're just looking at this piece. Okay, so when I do that, I've put some brackets here to differentiate that we're just focusing on that integral. Okay, so focusing on that integral, u times v is t times 1/5 e to the 5t minus the integral of v u prime, so minus the integral of v, and u prime is just 1. Okay, so I think we're going to clean up just a little bit more. Maybe I ran out of space. The important thing here to notice is that I've finally gotten to a point where I can easily anti-differentiate 1/5 e to the 5t. That antiderivative is essentially here, except I've cleaned up by also multiplying by minus 2/5. Okay, so I'll let you make sure that you believe that I got the right answer here. From here to here was simply evaluating this antiderivative and then distributing the minus 2/5 and cleaning things up. This third example initially doesn't look like it's a good candidate for integration by parts. We want to find an antiderivative for the natural log of x. It doesn't look like a candidate for integration by parts, but it will if we write it a slightly different way. So I'm simply going to write log of x as log of x times 1. And then I have parts, even though one of those parts isn't doing very much. And I'm going to pick log x to be u, and I'm going to pick 1 to be v prime. And then just as in the first two examples, we're going to calculate the other pieces of the puzzle. So we have u as log x, and we have v prime as 1. The derivative of u is 1 over x, and an antiderivative for 1 is x. So I have the four pieces that I need, and we're going to take all of those and plug them into the integration by parts formula. And so out here we have u times v, log x times x, minus the integral of v, which is x, times u prime, which is 1 over x. And notice what happens in this new integral. The new integral simplifies to be something very simple. X times 1 over x is simply 1. And so now this is easy to antidifferentiate. I antidifferentiate 1, and I simply get minus x. So an antiderivative for log x is x log x minus x plus that constant of integration.